For almost 2,000 years, the dark patches on the moon's face had a name: Maria, seas. The educated observers of the ancient and medieval worlds, the people whose job it was to understand the sky, believed those dark patches were actual bodies of water, liquid oceans on another world. This was not a fringe view, it was the consensus view, defended by serious astronomers across 13 centuries, and it persisted in scientific discussion into the 1800s. The maps in the great observatories named the seas individually: the Sea of Tranquility, the Sea of Serenity, the Ocean of Storms. Those names are still on every moon map today, and they are names given by people who genuinely believed there was water in those basins. They were wrong, spectacularly wrong. And the way they discovered they were wrong, and the way every generation since has discovered that the previous generation was wrong about something, is what this video is actually about. Humans have been making recorded observations of the moon for at least 30,000 years. The modern scientific understanding of what the moon is, where it came from, and what it's made of is less than 50 years old. Almost everything we currently believe about the moon was discovered within the lifetime of someone who is still working in the field today. This is not a list of facts. It is a story about being wrong repeatedly in increasingly sophisticated ways. There are 5 paradigms in this story. Each one overturns the last. The 5th one is happening right now, and it is going to be overturned too. Let's go through it. The earliest lunar observation we can date is a carved bone, roughly 30,000 years old, found in the Abri-Blanchard rock shelter in southwestern France. The bone is marked with 69 notches arranged in a pattern that some archaeologists interpret as a lunar phase count across roughly 2 months. The interpretation is disputed. What is not disputed is that lunar phase tracking is among the oldest forms of recorded human knowledge, older than agriculture, older than writing, older than nearly anything else humans recorded. The reason matters. The lunar cycle is the most regular, most observable, most useful natural timekeeper available to a pre-literate culture. The phases repeat every 29.5 days. They are visible to anyone with eyes. They divide the year into roughly 12 recognizable segments. Every early calendar humans built, Babylonian, Egyptian, Chinese, Mesoamerican, used the moon as its primary reference. This produces the first paradigm: the moon as timekeeper, not as a place, not as an object with composition or geography, as a symbol, a clock in the sky, owned by whichever deity the local culture attached to it. The first discoveries against this paradigm came from the Greeks. Around 450 BCE, Anaxagoras of Clazomenae proposed that the moon shone by reflected sunlight rather than by its own light. This was a radical claim. It implied that the moon was a physical object, illuminated like a stone in sunlight, rather than a luminous being. He went further. He argued the moon had mountains and ravines, and that it was made of the same kind of material as Earth. For these claims, he was prosecuted for impiety in Athens and forced into exile. Around 270 BCE, Aristarchus of Samos used the geometry of lunar eclipses to estimate the moon's distance from Earth. His method was sound. His result, approximately 60 Earth radii, was within a few percent of the actual figure of 60.3 Earth radii. He was effectively right. Almost no one accepted his result for the next 1,800 years. Around 150 BCE, Hipparchus refined the measurement and produced a distance figure within 10% of the modern value of 400 kilometers. He also produced the first reasonably accurate measurement of the moon's diameter, roughly a quarter of Earth's, which is correct. These were extraordinary achievements. They were also, for the next millennium and a half, largely ignored. The dominant view across most of the world, through most of the medieval period, returned to the moon as symbol, as omen, as deity, as calendar, as anything except a physical place that could be visited or studied. The first paradigm holds for roughly 30,000 years. The next paradigm arrives in a single year. In November 1609, an Italian named Galileo Galilei pointed a newly improved 20-power telescope at the moon and saw something that changed the field permanently. He saw mountains. He saw craters. He saw shadows that lengthened and shortened as the Terminator moved across the surface, exactly the way shadows lengthen and shorten on Earth. He used the shadow lengths to estimate the heights of the lunar mountains. His figure of approximately 4 miles for the tallest peaks was close to correct. The drawings he published in Sidereus Nuncius in March 1610 are, by modern standards, crude. By the standards of 1610, they were revolutionary. They established the moon as a physical world rather than a celestial symbol, a place with terrain, a geography that could be mapped. The next 3 centuries are the centuries of the lunar cartographers. Each generation extends the maps. Each generation revises the previous generation's errors. Each generation believes it is producing the definitive account. In 1645, Michael van Langren produced the first detailed lunar map with name features. Most of his names were political tributes to the Spanish royal court and did not survive him. In 1647, Johannes Hevelius produced a more comprehensive map with naming conventions that partially survived. In 1651, the Jesuit astronomer Giovanni Riccioli published the map whose naming convention became the standard, naming the dark patches as seas and the craters after philosophers, scientists, and saints. Roughly 200 of the names Riccioli assigned in 1651 are still in use today. The names you read on a modern moon map were chosen by a 17th century Jesuit. Throughout this period, the question of what the Maria actually were remained unsettled. Some observers maintained they were genuine bodies of water. Some argued they were dried lake beds. Some proposed they were vast plains of volcanic ash. The telescopes of the era could not settle the question. The decisive observation came from a spectroscopy in the late 1800s. By analyzing the light reflected from the lunar surface, astronomers detected no signature of atmospheric absorption, meaning the moon had no detectable atmosphere, and an airless world cannot retain liquid water on its surface. The Maria, whatever they were not seas. The naming survived. The interpretation did not. There is one more discovery from this era worth marking because it shaped the next century. In 1837, the German astronomers Wilhelm Beer and Johann Heinrich Mädler published a lunar map of such accuracy that it remained the standard reference for the rest of the 19th century. The map was paired with an explicit claim that proved enormously consequential, that the moon was a dead world, no atmosphere, no water, no change, no geological activity, a frozen artifact unchanged since its formation. That claim, the moon is dead, was the consensus view for the next 130 years. It was wrong in several specific ways that we'll get to, but it shaped how the early space age approached the moon. The second paradigm, the moon as place. A geographic object mappable, measurable, and, in the consensus of the late 19th century, finished. A corpse hanging in the sky. The first half of the 20th century produced relatively few major lunar discoveries through observation alone. The telescopes had reached the resolution limits that Earth's atmosphere imposed. The major questions about the moon, its composition, its interior, its origin, could not be answered from the surface of another planet. What changed everything was the possibility of going there. On September 13th, 1959, the Soviet Union's Luna 2 became the first human-made object to reach the lunar surface. It did not soft land. It struck the moon at roughly 3.3 kilometers per second, as designed. The achievement was the navigation, hitting a target 384,000 kilometers away with the guidance technology of 1959. 3 weeks later, on October 7th, Luna 3 returned the first photographs of the lunar far side. The images were grainy. The transmission was incomplete. They resolved roughly 70% of a hemisphere that no human had ever seen. And what they showed was the first paradigm-shifting discovery of the space age. The far side was different, not subtly different, substantially structurally different. The near side is roughly 31% covered by the dark mare basalts. The far side is roughly 1% covered. The far side crust is, on average, around 15 kilometers thicker. The two hemispheres of the moon were not the same world. No prior theory had predicted this. Every model of lunar formation that existed in 1959 had assumed the moon was, in broad terms, symmetric. The Luna 3 images forced the first major revision of the space age. Whatever process formed, the moon had produced a body with two distinctly different faces, and the existing theories could not explain why. Remember this as symmetry. It is going to come back twice more in this video, in 2012 and in 2019, and each time it returns, the explanation will have shifted. The American response to Luna was the Ranger program. Between July 1964 and March 1965, 3 Ranger spacecraft returned more than 17,000 high-resolution images during their final approach to the lunar surface, taking pictures right up until impact. The images resolved features as small as 30 centimeters. They revealed that the lunar surface, at the scale where landings would have to occur, was substantially rougher than the lower resolution observations had suggested. The Surveyor program between June 1966 and January 1968 soft-landed 5 spacecraft on the lunar surface. Surveyor 1's first image, a robotic footpad resting on lunar regolith, answered a question that had been debated seriously for decades. In 1955, the astronomer Thomas Gold had proposed that the lunar surface might be covered in fine dust so deep that any landing craft would sink into it, possibly by tens of meters. The Surveyor landings demonstrated that the regolith was firm enough to support a spacecraft. The dust layer was real, but it was centimeters deep, not meters. The Apollo landings could proceed. In parallel, the Lunar Orbiter program, 5 spacecraft between August 1966 and August 1967, photographed 99% of the lunar surface at resolutions sufficient to select Apollo landing sites. These photographs remained the highest resolution global lunar imagery available until the Lunar Reconnaissance Orbiter 4 decades later. The third paradigm forms in this period: the moon as a target, an operational destination, a place to be reached, photographed, characterized, and ultimately landed on. The question shifted from what is the moon to where on the moon can we safely operate? And then, in July 1969, the paradigm shifted again. Apollo 11 returned 21.5 kilograms of lunar material to Earth. Across the 6 successful Apollo surface missions, the program returned 382 kilograms of lunar rocks and soil. The Soviet Luna sample return missions added another 326 grams between 1970 and 1976. That material, analyzed in laboratories across the world for the next 55 years, and counting, produced more revisions to the consensus view of the moon than the entire previous history of lunar science combined. The story of those revisions is best told as a single sequence because each finding set up the next, and the cumulative pressure of the findings produced the largest paradigm shift in the field. It began with the dates. The oldest highland rocks returned by Apollo dated to roughly 4.46 billion years old, only about 100 million years younger than Earth itself. The Mare basalts dated between 3.1 and 3.9 billion years old. The moon was not a young object captured into Earth orbit late in the solar system's history, which was one of the leading theories before Apollo. The moon was nearly as old as Earth, and it had been geologically active in its early period, molten enough to produce vast lava flows that filled the impact basins and created the Maria. That finding raised a question. If the moon was as old as Earth, where had it come from? The composition data offered a clue, and the clue was strange. The lunar rocks matched Earth rocks in their oxygen isotope ratios, specifically the ratio of oxygen 17 to oxygen 16, to within measurement precision. This match is significant because oxygen isotope ratios vary measurably between different bodies in the solar system. Mars rocks have a different ratio. Asteroid samples have different ratios. Meteorites from the outer solar system have substantially different ratios. The moon's match with Earth was so close that it implied either a shared origin or a shared formation region. But the lunar rocks were also different from Earth in a specific way. They were depleted in volatile elements: water, sodium, potassium, zinc, by factors of 3 to 10 compared with terrestrial averages. Whatever process had formed the moon had occurred at temperatures high enough to vaporize the lighter elements and drive them away. The Apollo samples were also remarkably dry. The consensus reading of the data through the 1970s and 1980s held that the moon contained essentially no water at all, that it was, at the parts per million level, the driest body that had ever been measured. We'll come back to that finding in the next act because it turned out to be substantially wrong in ways the Apollo analytical techniques could not detect. And then the seismometers spoke. The Apollo missions left 5 seismometers on the lunar surface, operating between 1969 and 1977. They recorded more than 12,000 events: moonquakes, meteoroid impacts, and the controlled impacts of spent rocket stages. The waveforms from those events revealed that the moon had a layered interior, a crust averaging around 50 kilometers thick on the near side and thicker on the far side, a mantle, a partially molten lower mantle, and at the center, a small iron-rich core, roughly 330 kilometers in radius. The moon was not a homogeneous ball of rock. It was differentiated, separated by density into layers, which meant it had once been entirely molten, the whole body, hot enough to fully liquefy. Now the findings converged. The moon was nearly as old as Earth. Its oxygen isotopes matched Earth's. Its volatiles were depleted by high-temperature processing. It had been fully molten in its early history. And it had a small iron core, much smaller than Earth's relative to body size. Only one origin scenario fit all of those constraints. The giant impact hypothesis, proposed in 1975 by William Hartmann and Donald Davis, and refined through the 1980s, held that the moon formed when a Mars-sized body, sometimes called Theia, collided with the early Earth approximately 4.5 billion years ago. The impact ejected material from Earth's mantle into orbit, where it coalesced over a period of perhaps months to centuries into the moon. This explained the findings. The matching oxygen isotopes because the moon was largely made of Earth material. The volatile depletion because the impact was hot enough to vaporize light elements. The fully molten origin because the post-impact body was entirely liquid. The small iron core because most of Theia's iron had merged with Earth's, leaving the moon iron poor. The giant impact hypothesis is, with modifications, the current consensus. It has been challenged repeatedly across the last 50 years. It has been refined to account for findings the original version did not predict. But the central claim, that the moon is, in substantial part, made of Earth, has held. This was the largest single revision in the history of lunar science. For most of human history, the moon had been a separate object, a companion, a symbol, a place. After Apollo, the moon became, in a literal sense, a piece of Earth that had been blown off in an ancient catastrophe and never came home. The fourth paradigm, the moon as sample. An object whose composition, age, and origin could be measured directly, and whose measurements forced the revision of nearly every prior theory about how it had come to be. Apollo ended in December 1972. The Soviet Luna sample returns ended in 1976. For the next 2 decades, no spacecraft returned to the lunar surface. When the mission started again, in the late 1990s, they overturned one of the central findings of the Apollo era. In 1994, the American Clementine mission entered lunar orbit. It carried a radar instrument that returned signals from the permanently shadowed regions near the lunar poles, craters where the sun has not shone in billions of years. The signals were consistent with the presence of water ice. The result was controversial. The Apollo samples had established that the moon was dry. For 20 years, the moon is dry was a foundational fact of lunar science. The Clementine finding was treated as a possible instrument error. In 1998, the Lunar Prospector mission confirmed it. Its neutron spectrometer detected high concentrations of hydrogen at both poles. This was the first major revision of the post-Apollo era. The moon was not dry. In the floors of polar craters, where temperatures never rise above minus 170 degrees Celsius, 100 Kelvin, there were billions of tons of water ice. The finding produced a cascade of missions. Japan's Kaguya in 2007, China's Chang'e-1 in 2007, India's Chandrayaan-1 in 2008. In 2009, NASA's L-Cross mission deliberately crashed an upper-stage rocket into the floor of Cabeus crater at 2.5 kilometers per second. It flew a second spacecraft through the resulting debris plume. The analysis was definitive. The plume contained roughly 5.6% water by mass. To put that in perspective, the lunar soil at the polar craters is wetter than the soil in parts of the Sahara Desert. The water finding overturned one Apollo-era assumption. The next 2 missions overturned 2 more. In 2012, NASA's Grail mission, twin spacecraft flying in formation to map the lunar gravity field, produced the highest resolution gravity map ever made of any body in the solar system, including Earth. The map revealed that the lunar crust is substantially thinner on average than the Apollo-era seismic data had suggested. The near side crust averages around 34 to 43 kilometers thick. The far side crust averages closer to 60. The hemispheric asymmetry first seen by Luna 3 in 1959 was confirmed in detail, but it was also revealed to be more extreme than the previous generation of measurements had shown. The Moon's two hemispheres differ in crustal thickness by nearly a factor of 2. This raised again the question that Luna 3 had raised 53 years earlier. What process produced a body with two distinctly different faces? In January 2019, China's Chang'e 4 mission produced the first ever soft landing on the lunar far side, in the floor of the von Karman crater within the South Pole Aitken Basin. The South Pole Aitken Basin is the largest confirmed impact structure in the solar system, roughly 2,500 kilometers across and 13 kilometers deep, and its floor contains material excavated from the lunar mantle by the original impact. Chang'e 4's spectroscopic analysis of that material detected mineral signatures consistent with mantle-derived olivine and pyroxene. For the first time, the lunar mantle was being directly characterized at the surface. The findings revived a hypothesis that had been dormant since the 1970s. The South Pole Aitken impact may itself be the reason for the lunar hemispheric asymmetry, an impact large enough to redistribute crustal material across the body and produce the two-faced moon. The hypothesis is not settled. It is one of several candidates currently under active research. But the Chang'e 4 findings are the strongest evidence in its favor in 50 years. The asymmetry that Luna 3 discovered in 1959 and that Apollo could not explain, and that Grail refined in 2012, may finally have an explanation. We are not sure yet. The answer will likely arrive within the next decade. The most significant revision to the dead moon consensus came in 2020 from the Chinese Chang'e 5 mission. Before 2020, the consensus, based on Apollo and Luna samples, was that lunar volcanism had largely ended between 3.1 and 3.9 billion years ago. The moon was thought to have cooled too quickly to sustain volcanic activity much later than that. Chang'e 5 landed in Oceanus Procellarum and returned 1.73 kilograms of material to Earth. The samples dated to 2.0 billion years ago. This was a 1 billion year revision. It proved that the moon remained geologically active for 1 billion years longer than the Apollo-era models predicted. The moon was not a piece of Earth that died early. It was a world that stayed alive far longer than our best theories could explain. And we still do not know what kept it alive. The standard models predict that a body the size of the moon should have cooled to volcanic shutdown long before 2 billion years ago. Something kept it warm. We do not yet know what. The discoveries continued to pile up. In 2020, the SOFIA Airborne Observatory detected molecular water, actual H2O, not just hydroxyl, on the sunlit lunar surface in Clavius crater at concentrations of 100 to 400 parts per million. In 2023, India's Chandrayaan-3 successfully landed near the South Pole. Its thermal probe, CHE-STE, revealed a startling temperature gradient. The surface was a relatively warm 70 degrees Celsius, but the temperature dropped to minus 10 degrees Celsius just 8 centimeters below the surface. The lunar regolith is a more powerful insulator than we had ever measured in a lab. The implications for future lunar habitats are substantial. A base buried by less than a foot of regolith would be thermally stable in ways that no engineering on Earth currently provides. The fifth paradigm, the moon as resource, is where we are now. The moon is no longer just a place to be studied or a sample to be dated. It is a body containing materials, water ice for life support and propellant, oxygen-rich minerals, regolith with measurable thermal insulation properties, that the next century of human spaceflight is being built around. That is the pattern. For 30,000 years, the moon was a symbol. Then the telescope made it a place. The rockets made it a target. Apollo made it a piece of Earth. And the modern era has made it a resource. Each of these paradigms was built on the ruins of the one before it. Each generation of scientists looked at the data they had and reached a conclusion they believed was final. The Maria are not seas. The moon is not symmetric. The moon is not dry. The moon did not die 3 billion years ago. Each of those statements was once a fact in a textbook. Each of them was eventually proven wrong by a new instrument, a new sample, or a new perspective. I want to give you one more because this one is happening right now and you are watching it land in real time. In the last decade, a series of missions and reanalyses have established that the moon almost certainly had a magnetic field for the first billion or so years of its existence. The evidence is in the lunar swirls, pale, ribbon-like markings visible on the surface, scattered across both hemispheres, that appear to be regions where ancient magnetic anomalies are deflecting the solar wind and preventing the normal darkening of the regolith. They look like fingerprints on the moon's face. The Apollo-era consensus held that the moon was too small and too cold ever to have generated a magnetic field. That consensus is now collapsing. The current question is not whether the moon had a field, but how a body the size of the moon managed to sustain a dynamo at all, and for how long, and why it shut off. Somewhere in the textbook chapter that contains those swirls, there is a sentence that is as wrong as the seas of water were in 1651. We do not know which sentence it is yet. But the next decade, the Artemis landings, the permanent lunar bases, the deep crater explorers, the samples from the far side that we have not yet brought home, will find it. And this is the part I want you to actually hold on to. The story of the moon is not the story of a list of facts that we have finally gotten right. It is the story of a species that keeps looking up, keeps building better instruments, keeps going further, and keeps discovering that the generation before us was wrong about something they were certain of. Anaxagoras was prosecuted for claiming the moon was a stone. Riccioli mapped seas that were not seas. Beer and Madler announced a dead world that was not dead. Apollo declared a dry moon that was not dry. Every one of them was the best science of their era. Every one of them was wrong about something fundamental. The people who will overturn our current consensus are alive right now. Some of them are graduate students. Some of them are still in school. Some of them are watching videos like this one, working out what they want to spend their lives on. That is the pattern. That is what the moon has been teaching us for 30,000 years. The story is never finished.